In this video, we will be discussing the fundamental theorem of calculus. We'll start with the fundamental theorem of calculus part 1, or theorem 1, that let f be a function that's integrable on the closed interval ab. And for each x in ab, let f of x equal to the integral from a to x of f of t dt. Then capital F is uniformly continuous on the closed interval AB. Furthermore, if little f is continuous at C in AB, then capital F is differentiable at C, and we have this formula for the derivative of capital F at C, and it is equal to f of C. We have this alternate form of this theorem right here as well. And we have a quick example, which we will go through in more detail later in this video. Then we have this corollary based on the chain rule. Let little f, be continuous on AB, and let G be differentiable on CD, where the image of CD with respect to the image of CD given G is a subset of AB. So we're going to define capital F as being the integral from A to G of x of f. Then capital F is differentiable on CD, and the derivative of capital F is equal to f of g of x times g prime of x. And we have this one example here, which we will work out in more detail as well as others later in the video. Next, we have the fundamental theorem of calculus part 2, the second theorem. And this is one you're probably familiar with, very familiar with, from first year calculus. So if lowercase f is differentiable on AB and f prime is integrable on AB, then the integral from a to b of f prime is equal to f of b minus f of a. Again, we have an example which we'll go through, and many more other examples. Last, we will look at the improper integral. If a function lowercase f is defined on the half-open interval ab and integrable on cd for every c in the half-interval ab, if the limit as c approaches a from the positive side of the integral a to c of f exists, then the improper integral of f on the half-open interval a to infinity, denoted integral a to infinity of f, is given by the limit as c approaches infinity of the integral a to c of f. And we have a couple of examples here which we will go through in more detail as well as others. First, we will look at the fundamental theorem of calculus part 1. If f is a function integrable on the closed interval ab, and for each x in the closed interval ab, we are going to let f of x, this capital F of x, equal to the integral from a to x of f of t dt, then this capital F, which we have defined as the integral of f of t, is continuous on AB, and furthermore, if little f is continuous at C, then f is differentiable at C, and this capital F prime of C is equal to f of C. And our first example is if we have capital F of x is defined as the integral from 0 to x of square root of 5 plus t cubed dt for x greater than 0, then f prime of x, using this formula here, so this form tells us that our f of t is equal to the 5 plus t cubed. So when we want the derivative of capital F of x, we just need to evaluate f at x. So the derivative of capital F of x is equal to the little f evaluated at x, which will give us the square root of 5 plus t cubed. This is the alternate form, d dx, of the integral 0 to x of square root of 5 plus t cubed. So here is our little f of t, and we plug in x in for t. The proof of this theorem will first start by showing that f is uniformly continuous, proving this first statement. And then the last part will be to show that the derivative of capital F evaluated at c is equal to the lowercase, this function little f at c. And to show this, we're going to use the definition of the derivative and say f prime of c is equal to the limit of f of x minus f of c all over x minus c. So to start, we're going to show that capital F is uniformly continuous, and we're going to use the fact that little f is integrable on the closed interval ab. And since we're talking about a function on a closed interval, that must mean that that function is bounded on the closed interval. In other words, we can find a maximum. That is, there's a capital B, we'll call it capital B greater than 0, such that the absolute value of f of x is less than or equal to our capital B for all x in the interval AB. My claim now is that capital F of x is uniformly continuous on the closed interval AB. And so I'm just going to remind you what it is to be uniformly continuous. So a function is uniformly continuous if for every epsilon there exists a delta greater than 0 such that the distance between f of x and f of y can be made arbitrarily small, can be less than any epsilon you want to give me, whenever the distance between x and y is less than delta. So give me an epsilon, and I can give you a delta, and such that if you keep the distance between x and y less than delta, then the distance between f of x and f of y will be less than epsilon. And of course, epsilon has to be greater than 0. Applying this definition to our particular proof, that means if we want to show capital F of x is uniformly continuous, given any epsilon greater than 0, if x and y are in AB, and so here I've kind of drawn what's going on here. X and y are both points in AB, and I have x less than y. And the distance between x and y is less than delta, I can come up with a delta equal to epsilon over b. So again, epsilon is the one that's given, and b is our maximum value of f of x. Then capital F of y minus capital F of x, and now I'm going to use my definition of capital F of x, is equal to the integral, my f of x is integral a to x f of t dt. My f of y is going to be a to y f of t dt. But now looking at my drawing here, I'm integrating from a to y and also from a to x. And I'm subtracting the integral from a to x from the integral from a to y. So that's going to be equal to the integral from x to y f of t dt. And I still have the absolute values, but I can remove them or move them into the f of t, but then I have to do the less than or equal to, which is also less than or equal to. Now here, our absolute value of each f of t is less than b, so I can plug in my b, and then this here, this integral, will be equal to b times y minus x. And then as long as my difference between x and y is less than delta, and I choose my delta to be epsilon over b, then this whole thing here, the difference between the two functions, is going to be less than epsilon, and therefore f of x is uniformly continuous. Now we are ready to prove the second part, which is f prime of c is equal to little f of c, and I have that here, f prime of c is equal to little f at c, and this middle part here is just the definition of the derivative of f at c, and that definition is the limit as x approaches c, f of x minus f of c all over x minus c. And if you recall, this is the limit as x approaches c of the slope. So this here, right, is the rise, the difference in the y values over the run, the difference in the x values. And now we're going to use the fact that f is continuous at c for c in the closed interval AB. And how do we know this is true? Well, we're given that. It says if f is continuous at c in AB, then f is differentiable, etc. So f is continuous, and the definition of a function f continuous at c means that for every epsilon greater than 0, there exists a delta greater than 0 such that the f of x minus f of c is less than epsilon whenever x minus c is less than delta. In other words, we can make the difference between f of x and f of c arbitrarily small by defining a delta, this condition that the difference between x and c is less than delta. So plugging in or using this definition in our example here, given any epsilon greater than 0, there exists a delta greater than 0 such that f of t minus f of c, in this case our variable for f is t, so f of t minus f of c is less than epsilon whenever t is in AB, and t minus c is less than delta. Looking at what we want to prove, so I've written this portion over here. We're looking at the limit as x approaches c of f of x minus f of c over x minus c. We want to prove that this limit is equal to f of c. So using this definition of a limit, so L is a limit of f at c if for each epsilon greater than 0 there exists a delta greater than 0 such that the difference between f of x and the limit is less than epsilon. In other words, it can be made arbitrarily small whenever x is in D, and the difference between x and c is less than delta. So I need to find, for every epsilon, I need to find a delta that can make the f of x minus L, this f of x minus my limit, less than epsilon. So I'm going to look at f of x minus L, which I've rewritten here, and I've pulled out the x minus c from this part, and I use the definition of f of x, capital F of x and capital F of c, which I get up here from my fundamental theorem of calculus. So I have converted that to the integral from a to x f of t dt, and then minus f of c, plugging into here, that's the integral from a to c f of t dt, and then I have my minus f of c, and this is all an absolute value. I want to somehow combine my f of c with these other terms here. So I note that f of c is a constant, so we can rewrite f of c equal 1 over x minus c, the integral cx f of c dt. And why can we do that? Well, if we look at this portion here, the integral from c to x of f of c dt, f of c is a constant, so we can pull it out of the integral, and we're left with the integral c to x of 1 dt, which is equal to t evaluated at x and c times the constant. So we have f of c x minus c. If I divide this side by x minus c and this side by x minus c, I get this equation here. So here I have substituted my f of c with this equation, and I have my absolute value of x minus c integral, and here I combine these two sort of in the same way I did up here when we were proving f was uniformly continuous. So I combine these two integrals to be the integral from c to x of f of t dt, and then I also have now my f of c is equal to 1 over x minus c integral from c to x f of c dt. To go from this line to this line, I simply have the absolute value of a product, and I changed it to the product of two absolute values, and that's less than, and now I moved the absolute value inside the integral. And I did that because now I can use this fact over here that f of t minus f of c is less than epsilon. So I can then have my less than sign here and plug in epsilon. And what I'm left with after I take out that, I still have my integral of from c to x of 1 dt, and that'll evaluate to be x minus c. These two cancel out, and what I'm left with is epsilon. So that means my function, my derivative, f prime of c, which is defined here, is equal to my limit, or minus my limit is less than epsilon, which means my f prime of c is equal to f of c. And I've proven what I needed to show. Next, we have this corollary. Let f be a continuous function on AB. So here's AB. And let g be differentiable on the interval CD, where g of CD is a subset. Once we map from CD using g, we get it into AB. So define capital F of x equal to the integral from a to g of x of f for all x in CD. Then f, capital F, is differentiable on CD, and f prime of x is equal to f of x g of x times g prime of x. For our proof, I'm going to start by letting f of x equal to the integral from a to g of x f of t dt. And here I did put in a variable, my variable of integration as being t, just to remind myself that my variable of integration is not x. So for example, if g of x is equal to x squared, then f of x could be equal to the integral from a to x squared of f of t dt. Anyway, so this is just an example to give me a sense of what's going on. So I can integrate t, and whenever t, after I integrate, I plug in the variable x squared. So my variable of integration is not x, but here it's t, and this could be x. So anyway, going back to the proof. So again, this is an example. It's not really part of the proof. I just wanted to see what was going on. So anyway, let g of x now equal to the integral from ax f of t dt. You can see how this is related to our f of x. The only difference is instead of g of x over here as the upper limit of integration, I have x. But now I can compose g, capital G, with lowercase g of x. And if I plug in lowercase g of x here for x, I get my capital F of x. So take a look and see what's going on there. So we're going to note that f of x is equal to capital G composed with little g of x. And by the chain rule, the derivative of capital X is going to be the derivative of capital G of x, with g of x inside, times g prime of x by a normal chain rule from first year calculus. Now, applying the fundamental theorem of calculus here, if I have g of x is equal to the integral from a to x of f of t dt here, that means g prime of c is equal to f of c. So that'll be here. And again, this is just straightforward applying the fundamental theorem of calculus. So now I have g prime of g of x. If I plug that in, g of x for c, that would be equal to f of g of x. So what I have then is f prime of x is equal to g prime of g of x, which is f of g of x, times g prime of x. And just kind of underlining where everything came from. So our f prime of x, right, is equal to capital G prime of x of g of x. And that is what I have here underlined in blue. And then we have to bring down our g prime of x, our lowercase g prime of x. And that's it for the proof. And the example of this is that capital F of x equal to the integral from 0 to x squared of the square root of 5 plus t cubed dt. For x greater than 0, we want to find f prime of x. So our f of t in this case is equal to the square root of 5 plus t cubed. And our g of x in this case is equal to our x squared. So g prime of x is equal to 2x. Now by our corollary then, f prime of x is equal to f of g of x times g prime of x. So f of g of x, where is our little f? F of g of x is equal to f of x squared times g prime of x is 2x, and f of x squared is equal to the square root of 5 plus, and then x squared cubed is x to the 6th times our 2x, so our final answer will be 2x times square root of 5 plus x to the 6th. Now that we have that corollary done, we can look at our fundamental theorem of calculus part 2, which should be very familiar to you. If f is differentiable on the closed interval ab and f prime is integrable on the closed interval ab, then the integral from a to b of f prime is equal to f of b minus f of a. I am sure you know how to use it, but let's look at the proof, which is much shorter than the other proof for part 1. We are going to start this proof as we did many proofs involving Riemann sums, and that is with a partition. We're going to let p equal to a partition. It's equal to x naught, x1 up to xn. It's a partition of ab. Now by the mean value theorem, which I have written here for your reference, that if you have a continuous function on AB that is differentiable on the open interval, then there exists at least one point C in AB such that the slope, the derivative of f at C is equal to the slope between the points f of A and f of B. Applying that here to our partitions for each subinterval x sub I minus 1 to x sub I, we can obtain some point t of I in the interval such that the derivative of f evaluated at t of I is equal to f of xi minus f of xi minus 1 over xi minus 1. So we're looking for the points ti such that the slope of f at ti is equal to the slope between the two endpoints of the interval. And before we apply the mean value theorem, we have one more thing to look at, which is in the interval, since ti is in the interval, then the f of ti has to be greater than the minimum function value over the interval, and it has to be less than the maximum function value over the interval. And so then we can multiply each, the minimum times the length of the interval, the f of ti times the length of the interval, and the maximum of our function value times the length of the interval. And now we can apply the mean value theorem, which I have written here. I just kind of rearranged it algebraically, and I can substitute here, and I get this next line. Now, if we sum over all the i's, here we're going to have our lower sum, and here we have our upper sum, and here we have our sums from I equal 1 to n, f of x of I minus f of x of I minus 1. And now to combine these two, we need to change our index I. So if I want this to go from I, I'm going to have to then, with this index, subtract 1. So because from here, if I plug in 1, my first value should be x naught. So this will give me, if I subtract 1 from this index here, I'll get x naught as my first value. Similarly, my last value over here will be x of n minus 1, which is exactly what I would get when I plug in n to get my last value here. So now that I have these indices the same, so they're both f of x of I need to have my summation index the same, or I'd like to make a common summation index. And what they have in common is they both iterate from 1 up to n minus 1. So here I'm going to iterate from 1 up to n minus 1 of f of x of I, but then I also need to add f of x n in order to make this equal to the summation from 1 to n. So I'm just going to iterate to n minus 1 and then add my last term plus f of x n. Over here, if I want to iterate from 1 to n, I need to then take this, from 1 to n minus 1, I need to take out my x of 0 term, so I'm going to subtract, because this is a subtraction, my f of x0 term, and now I have my summation going from I equal 1 to n minus 1. So these two are the same, and in fact these two will cancel out, and what I'm going to be left with is f of x of n minus f of x naught. But remember, because this is a partition, my x naught is equal to a, so this is f of a, and my xn is equal to b, so this is my f of b. So my lower limit then bounds f of b minus f of a over my upper sum. And now, because f prime is integrable, my lower and my upper sum must be equal, which means that this integral from a to b of f prime must be equal to f of b minus f of a. For our first example, we note that the Fundamental Theorem of Calculus Part 2 requires f to be differentiable and f prime to be integrable. So we want to find a function f that is differentiable and f prime is not integrable. So for example, f of x is equal to x squared times sine of 1 over x squared for x not equal to 0, and 0 for x equals 0. You can see that f of x is differentiable. We can certainly take the derivative, and we did that in our chapter 6 when we looked at derivatives. So x squared sine of 1 over x squared, that's equal to g composed of f of 1 over g, where g is equal to x squared and f is equal to sine of x. So the derivative is equal to the limit of x squared sine of 1 over x squared, x minus 0, and that's the limit of, as x approaches 0, x of sine over 1 over x equals 0. So you can see the derivative is not bounded because of this x, and thus is not integrable. Our next example of the Fundamental Theorem of Calculus, Part 2, let f of x equal to x cubed, x in the real numbers. We want to find the integral from 1 to 4 of 3x squared. And we're going to note here our f of x is equal to x cubed, so f prime of x is equal to 3x squared, which is exactly what we're trying to take the derivative of. By the Fundamental Theorem of Calculus, over here, not the corollary, sorry, Part 2, right here, that means the integral from 1 to 4 of 3x squared is equal to f of 4 minus f of 1, which will be equal to 4 cubed minus 1 cubed equals 63. And really, if you were solving this normally, you probably would have just done the integration and gotten x cubed and then evaluated at 1 and 4, which is exactly what you're doing, but I did want to show you this form here since you want to get used to the notations of the fundament of this theorem. For our next example, we are going to prove the formula for integration by parts. So we're going to suppose that f and g are differentiable on the closed interval ab, and f prime and g prime are integrable also on the closed interval ab. We want to prove that the integral of ab of f times g prime is equal to f of b g of b plus minus f of a g of a minus the integral from a to b f prime g. So I've rewritten this statement here, what we want to prove over here, which is the integral from a to b of f g prime is equal to f of b g of b minus f of a g of a minus the integral from a to b f prime g. And that's equivalent to, if I just move this integral over to this other side of the equation, that the integral from a to b f g prime plus integral from a to b f prime g is equal to f of b g of b minus f of a g of a. And you can see, because of this f of b g of b and minus f of a g of a sort of follows this form here of the fundamental theorem of calculus part 2. So we will be using this fundamental theorem to do in our proof. We are going to define a new function h, which is just the product of f times g, so that h prime, using the product rule for derivatives, is equal to f g prime plus f prime g. By rules of differentiation, since f and g are both differentiable here by our the hypothesis of our theorem, then h, the product of these two, is also differentiable. Also, since f prime and g prime are integrable, that means h prime is integrable, since the product of two integral products are integrable. So if we look at the integral from a to b, h prime of t dt, so I just put in a variable of integration t, we have this form of our fundamental theorem of calculus, part 2. So by the fundamental theorem, we have that the integral from a to b, h prime of t dt is equal to hb minus ha. And then since h is just the product of f and g, that will be f of b g of b minus f of a g of a. Looking at this integral of h prime of t dt, so I have this written here, using this part of the product rule, this integral is equal to the integral from a to b of f g prime plus the integral of f prime g, again using the product rule. And now we also have that this integral is equal to f of b g of b minus f of a g of a. And here we have shown exactly what we wanted to prove. For our last topic, we have the improper integral. Let f be defined on the half-open integral ab and be integrable on the closed interval cb for every c in the half-open interval ab. So if the limit as c approaches a from the positive side of the integral of ac of f exists, then the improper integral of f on a to infinity, denoted integral from a to infinity of f, is given by this formula here. A to infinity of f is equal to the limit as c approaches infinity of the integral ac of f. So this is the formula we want for our improper integrals. For our first example, we are going to let f of x equal to x raised to the 1/3, and we are going to evaluate the integral of c to 1 for x to the minus 1/3, and the integral of 0 to 1 of x to the minus 1/3. This first integral, the integral from c to 1 of x to the 1/3 dx, is fairly straightforward. We take the antiderivative of x to the 1/3 to get 3/2 x to the 2/3 evaluated at 1 and c. So our final answer is 3/2 times 1 minus c to the 2/3. The second integral from 0 to 1 of x to the minus 1/3, we need to be a little more careful, because if you note, f of x, which is equal to 1 over x cubed, is not bounded on the interval 0, 1 because of the 0. There's a problem there. And therefore, it's not integrable on the interval 0, 1. And this is where we're going to start looking at the improper integral. Fortunately, it is defined on the half-open integral, 0, 1, and integrable on the half interval. So these are exactly the conditions for the improper integral. So f is defined on the half-open interval and integrable on the every c to b for c in the open interval. So that's exactly this condition here. So now we can use this formula here for the improper integral. So to evaluate the integral from 0 to 1, x to the minus 1/3 dx, we're going to look at the limit, and again using our definition, in this case as c approaches 0 of, and then plugging in here, 3/2, 1 minus c to the 2/3. Now as c approaches 0, we will get 0 here, and we'll just be left with the 3/2. Our next problem is let g of x equal to 1 over x for x in the half-open interval 0 to 1. So again, we have this problem when x is equal to 0. We want to evaluate the integrals c to 1 of 1 over x dx for x in the open interval, and also the interval from 0 to 1, 1 over x dx. The first integral is fairly straightforward. The integral from c to 1 of 1 over x dx. Taking the antiderivative, we have natural log of x evaluated at 1 and c, natural log of 1 minus natural log of c. This is 0, so we're left with minus natural log of c. Now when we consider the same integral going from 0 to 1, we note that 1 over x is not defined on the closed interval 0 to 1, and therefore 1 over x is not integrable on the closed interval 0 to 1. But 1 over x is defined on the half-open interval, 0 to 1, and integrable on the half interval, and that's where we use the improper integral definition. So the integral from 0 to 1 of 1 over x dx is equal to the limit as c approaches 0 from the positive side, because we're going from 0 to 1, integral of c to 1 over x dx, which from our previous work over here, that's equal to the limit as c approaches 0 from the positive side of minus natural log of c. And as c approaches 0, this will approach infinity. Therefore, our integral diverges to infinity, and we can write the integral is equal to infinity. Our next example is f of x equals x to the minus 2 for x greater than or equal to 1. So we have eliminated the problem of x equals to 0. So now we want to find the integral from 1 to infinity of f if it exists. So we look first at the integral 1 to c of x to the minus 2. And that's equal to minus x to the minus 1 evaluated at 1 and c. And we're left with 1 minus 1 over c. So now when we do this integral here, where we have this infinity, we use our improper integral formula, and we get that that's equal to the limit as c approaches infinity, plugging in our work from our previous example, 1 minus 1 over c. So as c approaches infinity, this approaches 0, and we're left with 1. Our last example is to look at g of x is equal to cosine of x for x greater than or equal to 0. So we'll consider the integral from 0 to c of cosine of x. So taking the antiderivative, we have sine of x from 0 to c, which is equal to sine of c minus sine of 0, which is just equal to sine of c. So if we wanted to look at this integral as c approaches infinity, since the limit of sine of c as c is approaching infinity does not exist, since it kind of bounces around between 1 and negative 1, then this integral from 0 to infinity of cosine of x dx is not an improper integral and has no meaning. We have finished the topics for the Fundamental Theorem of Calculus. First, we looked at the Fundamental Theorem of Calculus Part 1 that said if a function little f is integrable on the closed interval ab, for each x in ab, f of x is equal to, we define f of x to be the integral from a to x f of t dt. Then this capital F of x is uniformly continuous on the closed interval, and furthermore, if little f is continuous at a point c in ab, then capital F is differentiable at c. And then we have this formula that f prime at c, big F prime at c, is equal to little f of c. And we did this example here. Also, there's this alternate form of the Fundamental Theorem of Calculus Part 1. We did corollary for the chain rule that said, same conditions, f is continuous on AB, g is differentiable on CD, where g of the image of GCD is a subset of AB. Then if we define capital F to be the integral from a to g of x, again, this is this function g of f, then capital F is differentiable and f prime of x is equal to f of g of x times g prime of x. And we did this example over here. We had the Fundamental Theorem of Calculus Part 2. If f, again, the same conditions, f is differentiable on AB, f prime is integrable on AB, then if we define the integral from a to b, f prime, that would be equal to fb minus f of a. And we had a few examples, including this one here. And we also did the improper integral that said if we have an integral, so f is defined on the half open interval AB, and is integrable on CD for every C in the half interval AB, then if the limit as c approaches a from the positive side of a to c of f exists, then the improper integral, denoted the integral from a to infinity of f, is equal to the limit as c approaches infinity of the integral ac of f. For review, I have 2 problems for you to try, so you can pause the video, give them a try, and on the next slide I will have solutions for you. Here is the solution to the first problem and the solution to the second problem. And that's it for this video. Thank you for watching.